Hey, thanks for tuning in. Welcome to Nomadic Geek. Do you ever find yourself struggling with performance issues when dealing with multiple sensors? Or wondering if your server can handle the pressure of 12 or more camera feeds and a plethora of other sensors all at once? Well, in this episode, we'll be answering these questions and more. So sit back and get ready to take your surveillance system to the next level with the power of multithreading. Let's get started. In our earlier videos, we set up sensors and ESP32-CAM modules to string data through Websockets to our Node.js server. We also used TensorFlow.js for object detection on the server level and presented the data seamlessly on a single client interface in the web browser. If you haven't already viewed those videos, I strongly recommend doing so, as this tutorial builds upon the previous material. We will be using the code from our previous sessions and enhancing it with new modifications. While it is not mandatory to have prior knowledge of the earlier content, I highly encourage you to view them after this video for a comprehensive understanding of the project. In the future, I hope to be able to run the Node.js server on a Raspberry Pi 4B. Therefore, the focus of today's video is optimization and how to use limited performance hardware to handle it. These optimizations are, of course, essential for any setup, and we will explore techniques to improve the performance of our surveillance system and ensure that it runs smoothly even with limited resources. Multithreading is one such technique that can be used to optimize the system's performance. By using multiple threads, we can handle multiple sensors and camera feeds more efficiently. The Raspberry Pi 4 uses a Broadcom BCM2711 quad-core 64-bit CPU, up to 8 GB of RAM, and has built-in Wi-Fi and Bluetooth capabilities. The Raspberry Pi 4 is also energy efficient, making it a powerful yet sustainable choice for any setup. If you like this video, don't forget to give it a thumbs up and hit the subscribe button and notification bell so you know when I post more content. If you have any thoughts, questions, or feedback, please don't hesitate to share them in the comments section below. Stay tuned, and let's get started. We are using Websockets to establish communication between sensors and cameras and our Node.js server. This advanced protocol facilitates real-time, bi-directional data exchange, outperforming traditional request-response models. As a result, WebSockets excel in applications necessitating frequent updates or instantaneous responses. Multithreading is a sophisticated technique employed in computing to enhance performance by allowing multiple threads of execution to run concurrently within a single process. These threads, essentially lightweight, independent units of a program, can efficiently execute different tasks, maximizing resource utilization and expediting processing time. This approach is particularly effective in applications with diverse, asynchronous tasks, as it enables simultaneous execution, preventing one task from obstructing the progress of another. Consequently, multithreading substantially improves responsiveness, ensuring an optimal user experience. There are two main ways to handle multithreading in Node.js. In this tutorial, we will be using the module named cluster. The other one is called worker threads. In this video, we will not delve into the intricacies of worker threads. However, if there is sufficient interest, kindly leave a comment, and I will gladly produce a dedicated tutorial on this topic, guiding you through its implementation and usage. Round robin is a scheduling algorithm used to fairly distribute tasks among resources, such as multi-core processors. By assigning processes to different cores in a cyclic manner, it ensures balanced utilization of computational power. The algorithm maintains a circular queue of processes, giving each a fixed time slice for execution. As processes are dequeued, they execute on a designated core. If a process doesn't finish within its time slice, it returns to the queue's end, and the scheduler moves to the next process. In multi-core environments, round-robin scheduling ensures efficient resource utilization and prevents any single core from being overburdened, leading to enhanced system performance and responsiveness. We are starting by opening the code for the ESP32-CAM module from earlier videos. I have uploaded the same code for each module, just changing the port between each upload. So, we will start at port 8001 for the first module, 8002 for the second, and so on. We follow this pattern even for the Freenove module, as well as all the AZNV gas sensors. The only code change we have made for all these microcontrollers is the way we are sending the sensor data to the Node.js server. We are now separating the data with S:, followed by the readings for all the sensors, and C:, for all the commands for the module. Within the sensors.json file, which encompasses the configuration of sensor objects, the primary modification pertains to the quantity of sensors it accommodates. Presently, during server stress testing, I have incorporated all available sensors, for which I all possess power cables. Each module is characterized by its unique identifier, port, CSS class, display name, and accessible commands. As always in our project, the port serves as the distinct identifier for every WebSocket communication. Let's examine the server.js file. In addition to the familiar path, express, and WS modules, server.js now incorporates a few new imports, cluster and OS. The cluster module allows us to create child processes and make the most of multi-core systems for better performance and load balancing. The OS module offers utilities related to the operating system, such as system information and platform-specific details. Lastly, we have global sensor data, which acts as a dynamic container for sensor objects during server execution. This data structure keeps track of the sensor's state and configuration throughout the process. We also have our sensors configuration file included as always. I've introduced several noteworthy modifications to the server.js file. While I'll cover the most pertinent aspects, please don't hesitate to inquire in the comments should any questions arise. We now employ a set, rather than an array, for the connected client's variable. This change ensures that each WebSocket client remains unique, effectively preventing duplicate connections from accumulating. As a result, managing connected clients becomes more streamlined, since adding or removing clients from a set inherently preserves uniqueness. The constant update frequency dictates the rate at which the server refreshes clients with sensor object data. A value of 150 signifies an update interval of 150 milliseconds. By adjusting this figure, you can modulate the frequency with which clients obtain updates. A lower value yields more frequent updates, while a higher value leads to less frequent ones. The code also prints the number of logical cores recognized by the operating system. In the case of my computer, there are 16 cores. When working with multi-core systems, understanding the number of cores is crucial, as it enables you to optimize server performance through efficient task distribution among the available cores. I will make a change here to store the number of cores in a constant since it is reused several times in the code. Actually, we can discard number workers as it is now redundant. We can use cores instead. In this segment, we'll distributing sensors among worker instances to make the best use of our multi-core system. First, we calculate the number of sensors each worker should handle. We do this by dividing the total number of sensors by the available cores and rounding up the result. This ensures that every sensor is assigned to a worker. Next, we iterate through each core and assign a subset of sensors to a worker instance. For each core, we create a new array containing a slice of the main sensor array. If the new array is empty, it means there are no sensors left to assign, so we move on to the next core. We then create a new worker instance and send the first sensor from the new array to the worker to begin its assignment. We also set up an event listener to handle updates from the worker. Finally, we store the worker instance and its corresponding sensors port in a map for easy management and reference. This process allows us to effectively distribute the sensors among the cores and ensures optimal use of our system's processing power. Now, let's discuss this segment of the code which handles the scenario when a worker instance exits unexpectedly or crashes. We begin by setting up an event listener for the exit event on the cluster. This event is triggered when a worker instance is killed or exits for any reason. When the exit event occurs, we first log a message to the console, indicating that a worker has been killed and that a new one will be started in its place. Next, we remove the exited worker from the worker's map to keep it up to date. We then create a new worker instance using cluster.fork and calculate the sensor data it should handle. This is done by slicing the main sensor array based on the number of workers and the available cores. Once the sensor data is determined, we send it to the new worker using the update property with a value of sensor. This instructs the worker to start handling the assigned sensor data. Additionally, we set up an event listener for the message event on the new worker, ensuring that it can receive updates from the worker and update the sensors accordingly. Finally, we store the new worker instance and its corresponding sensors port in the worker's map, effectively replacing the exited worker and maintaining the optimal distribution of sensor management across cores. In this segment of the code, we set up a WebSocket server for the clients to communicate with and configure how the sensor data is sent to the connected clients periodically. First, we create a new instance of the WebSocket server, specifying the port on which it should listen, in this case, 8999. When the server is successfully initialized, a message is logged to the console, indicating that the WebSocket server is now listening for incoming connections. Next, we set up a recurring operation using the setInterval function. This function takes two arguments, a callback function and an interval in milliseconds, defined earlier as update frequency and 150 milliseconds. The callback function will be executed at every specified interval, allowing us to periodically send sensor data updates to the connected clients. Inside the callback function, we loop through all the clients in the connected clients set. For each client, we check if the WebSocket connection is in the open state, which means it's ready to receive messages. If the client's connection is open, we send the sensor data as a JSON string. The sensor data is first converted into an array of values using object.values and then wrapped in an object with the property called devices. This ensures that the clients receive the sensor data in a structured format, allowing for easy parsing and processing on the receiving end. In this segment, we handle new WebSocket connections, incoming messages from clients, and disconnections. First, we set up an event listener for the connection event on the WebSocket server. When a new connection is established, the callback function is executed, and the WebSocket instance representing the connection is passed as an argument. We add this WebSocket instance, WS, to the connected client set to keep track of all active connections. Next, we set up an event listener for the message event on the WebSocket instance. When a message is received from the client, the callback function is executed, and the message data is passed as an argument. Inside the callback function, we first check if the WebSocket connection is in the open state. If not, we return immediately without processing the message further. We then attempt to parse the received message data as JSON. If successful, we check if the operation property of the message object is set to function. If so, we look for the sensor to be updated based on the recipient property of the command object in the message. If the sensor is found, we determine the target worker responsible for the sensor by searching through the worker's map. We find the worker whose associated port matches the sensor's port. If the target worker is found, we send an update message to the worker with the command data. This instructs the worker to update the sensor based on the received command. Lastly, we set up an event listener for the close event on the WebSocket instance. When the client disconnects, the callback function is executed and the WebSocket instance is removed from the connected client set, ensuring that the server no longer attempts to send updates to the disconnected client. Finally, we define routes for the Express application, which serves as our HTTP server. We create two route handlers, one for the /client endpoint and another for the /client2 endpoint. When a client sends a request to either of these endpoints, the corresponding route handler is executed. For both route handlers, we use the GET method of the Express application to define a GET request. The first argument is the route path, and the second argument is a callback function that takes two parameters, the request object, _REQ, and the response object, res. Inside the callback function for the /client route, we send the client.html file located in the public /pages/client1 directory as a response to the client. We use path.resolve to obtain the absolute path of the file, ensuring it is properly resolved regardless of the file system. Similarly, inside the callback function for the /client2 route, we send the client.html file located in the public /pages/client2 directory as a response to the client. Lastly, we start the Express application by calling the listen method with the HTTP_port constant as the first argument. This binds the server to the specified port and starts listening for incoming requests. When the server starts, we log a message indicating the port number and the process ID of the server instance. Let's proceed with examining the sensor.js file, which represents each sensor, worker, and process in our system. This file will be executed once for each sensor registered in the sensors.json file, distributing the sensors to the available CPU cores according to the round-robin scheduling method, as explained earlier in the video and demonstrated in the server.js file. Sensors are assigned to cores one by one, and new instances are created when a sensor process dies. In the imported modules section, there isn't much new besides the mock model. The imported modules are utilized throughout the script to handle various tasks such as establishing WebSocket connections, performing object detection using the AI model, storing data in a JSON database, and working with the file system. The mock model is a custom module designed for testing purposes. It is used when you don't want to perform the computationally intensive task of loading the object recognition model. This allows for faster testing and debugging without the overhead of the actual AI model. Continuing with the code and some important variables and constants in this section. Test mode. This variable is used to set the code into test mode, for example, to load the mock model instead of the real model, which we will see further down in the code. Sensor. This variable represents the specific sensor that this particular worker or cluster instance handles. It will be updated with data from the main code in server.js. Command. This variable stores the command sent from the client to the sensors. When a microcontroller has a pending command, it is set for this specific worker. Threshold and frequency. These constants have been moved from individual camera sensors to the settings in the instances, as there was no need for different cameras to have different values for these settings. Valid entities. This variable still stores the objects that the object recognition should detect, but now it is based on the folders created under the images directory. This way, we don't have to explicitly specify what we want to have saved, but just create folders for, as an example, person, mice, or cat. Initial data received and resolve initial data are new and are used to keep track of the promise that is resolved when the sensor has received the first dataset, which we will see further down in the code. Here, we're working with the file system to determine the valid entities that the object recognition system should detect, as mentioned. These exception functions are the same as before, so we keep moving down the code. In this section, we set up an event listener to handle incoming messages from the main process. When a message is received, we process the message based on the message.update property. If the update type is sensor, we store the message's data in the sensor variable, which represents the current sensor this worker is managing. A message is logged to the console, indicating that the connection is prepared for the sensor. Subsequently, we call resolve initial data to resolve the initial data received promise, signifying that the initial data has been received and is ready for processing. If the update type is command, we save the message's data in the command variable, which holds the command sent from the client to the sensors. A message is then logged to the console, stating that a command is set to be executed for the current sensor. By setting up this event listener, our worker can react to incoming messages from the main process and update its internal state accordingly. This ensures smooth communication between the worker and the main process, enabling seamless coordination between them. The load model function is more or less the same as before. The main difference is that it now takes the argument text mode that I described earlier and uses the mock model instead of the real one if we have the text mode set to true. The main function is the core code of this file. It first awaits the initial data received promise to resolve before it starts to load the AI model. The promise is, as mentioned, resolved when the first sensor data is sent from the server.js file, which instantiates the sensor.js worker. If there are no sensors, the worker kills itself or continues further if the sensor is actually set. We create a WebSocket server for the particular sensor worker and wait for a connection. There is not much new when it comes to handling the object detection predictions or image data sent from the camera modules for incoming WebSocket messages. However, in the else statement that represents all other data, such as sensor data and commands, we have a few differences. Here, we work with the text data that comes from the WebSocket connection. Our goal is to update command and sensor information. First, we create two patterns to find the command and sensor data in the text. Then, we use a loop to look for command data. When we find it, we break it down into key value pairs, loop through them, and update the command state in the sensor object. Next, we set up an empty object to store the sensor data. We use another loop to search for sensor data in the text. Just like with command data, we break it down into key value pairs, loop through them, and update the sensor object. Once this code runs, the sensor object will have the most recent command and sensor data from the WebSocket connection. Then we update the main process, the server.js, about the sensor. We start the server. We can see the sensors are being loaded. We can observe that all the WebSocket servers have started on their respective ports. Additionally, we can see that the connections are initially prepared. This occurs when the sensor.js instance retrieves sensor data from the server.js file. Subsequently, a message indicating the connection has started. Here, I encountered an issue where my modules were not receiving sufficient power to start. It took me some time to determine this. But there you have it. This concludes this episode of the tutorial series. If you enjoyed what you saw, make sure to hit the subscribe button and give this video a big like. That way, you'll never miss a single one of my future uploads. And if you have any ideas for topics you'd like to see me cover in the future, drop a comment below. Your feedback and suggestions are always appreciated. So until next time, farewell and keep on learning.